Hello. Now we are going to talk a bit about how parametric equations connect to projectile motion. So we're going to be doing a projectile motion application problem here. And we have these two formulas, x and y, which are projectile motion parametric equations. And using more advanced mathematics than you currently can handle, and neglecting air resistance. So just saying, hey, we're not getting too physical about the physics of this. These two following equations describe the path of a projectile propelled upward at an angle of theta. And that angle of theta, depending on our initial height, that angle of theta is with the horizontal. So if we were at an initial height here, the projectile goes up and then maybe back down. There's a angle of theta with the horizontal. So our initial height, h, and an initial speed or velocity, v sub 0, or rather v naught, measured in feet per second. And of course, we could change this and have this in meters per second of metric if we wanted. So generally what we say is x equals v naught cosine theta. That's my coefficient on t. And y equals that initial height plus the vertical velocity times time minus 16t squared. So essentially we're thinking about velocity cosine being horizontal and velocity sine being vertical. So x horizontal, y vertical. And this negative 16, that represents the constant acceleration due to gravity. So this is a constant. You're going to see that negative 16 in a lot of problems. And when we are in imperial units, we'll have negative 16. If you were in metric units, you'd see a negative 9.8 here. So that is negative 16 feet per second squared. We have a velocity, feet per second, and then a height, just feet. If we were again in metric, that would be negative 9.8 meters per second squared. All right, so x and y, they give a position or a location of an object, horizontally or vertically, at time t in seconds. So let's look at using these two parametric setups and solving an application problem with a projectile, specifically a ball, which is thrown from a certain height. In this example, we have a baseball thrown from an initial height of 6 feet with an initial speed of 100 feet per second at an angle of 45 degrees with the horizontal. So let's think about what we're dealing with here. We're at an initial height of 6, and we are leaving that position, right? We're going up and then back down. That initial angle is 45 degrees. So what we're going to deal with is we first want to find the parametric equations x and y, which define the position horizontally and vertically, x and y, of the ball at time t in seconds. So for x equals v naught. My initial velocity is 100, and then we'll say cosine of theta is 45. So 100 cosine 45 t, and my y value, that's going to be my initial height, 6, plus my velocity, 100 times sine of 45 t, and then we'll have minus 16 t squared. So all I did was use my given information and I plugged those into my two formulas. At this point, I can simplify. So I'm going to go ahead and simplify. We know that cosine of 45 is root 2 over 2. So I have x equals 100 times root 2 over 2t, or rather, we have x equals 50 root 2t. And then my y equation, y equals 6 plus 100 times root 2 over 2, because that is sine of 45. It's the same as cosine. T minus 16t squared, or rather y equals 6 plus 50 root 2t minus 16t squared. And now we have two parametric equations that represent the position of the ball at time t. So we have a horizontal position and a vertical position, both with respect to time. Part B. Let's find the height of the ball after 1 second, after 2 seconds, and then also after 3 seconds. So the height, which equation should I choose? Well, the height is a vertical measurement off the ground, so we're going to use that y value. Y sub 1 will be 6 plus 50 root 2 times 1 minus 16 times 1 squared. Now we can calculate y sub 2 and y sub 3 very similarly. I'm going to write that out. So you guys should get the same information on your paper. I'm plugging those values into your calculator. You get three values. We have 60.71, 83.42, and 74.13, all rounded to the hundredths place. Now, this is an application problem, and when we're working on an application problem, every answer must have units. So what would be the units on y? Well, remember, y measures position, and we're measuring position in this situation, or distance, within feet. So this is how high, specifically, the ball is off the ground or above the ground. Part C of this question asks us to determine how long the ball is in the air. How long? What does that mean we should find? In this situation, that means we need to find time. So that must mean we know either an x or a y output value, because we need to be able to find t. So we need one of the other variables. Well, x and y represent a position. What do we know about position when the ball is not in the air, when the ball lands on the ground? When the ball lands on the ground, the height is equal to 0. And the height is measured by, we just found, y. So that means y would be equal to 0. So this is solving the equation 0 equals 6 plus 50 root 2t minus 16t squared. So we need to solve this quadratic equation to find the zeros. There will be two solutions, or one repeated solution if there's a spot where it hits the ground. You guys should feel very confident using the quadratic formula at this point. I'm going to work that out for us. Working through the quadratic formula as I've set up here, we get two t values. So we get t equals negative 0.083 or t equals 4.50. Now, can we have negative time? Not unless you are Marty and Doc. So in this situation, we determine that the ball hits the ground at t equals 4.5, and that unit of measurement on time in this case is seconds. So the answer is the ball hits the ground at 4.5 seconds because it has a height. My y value is equal to 0. Right, part D. Now I've rewritten both my x and y equations on this screen. So for part D, we're asked to determine the horizontal distance. Horizontal distance means we want to find x. So I'm going to come over here to my x equation. If I want to find x, that means I must know my time value. When does the ball stop? Ideally, the ball stops when it hits the ground. Now, of course, we know in the real world that ball would hit the ground and maybe roll or go into the ground a little bit. But here it's just going to stop when it hits the ground. So that would be at t equals, what t time did we find? 4.5 seconds. So at t equals 4.5 seconds. Now I encourage you to use the answer button in your calculator to find this value exactly without rounding. So the button or the value that I had found was 4.502700732. So you can use that. That would give you something that's accurate enough that you won't have a rounding error. Or, again, use that answer feature. So in this case, we have x equals 50 root 2 times that t value, which was 4.502700732. So I wrote that in my calculator. This is, or as it appeared in my calculator, this is a rounded value. The calculator cut off some decimal places. So this is still going to be not exactly correct, but it'll be close enough that you won't make an error on your homework. And evaluating this, I used the answer feature, but I get 318.39 feet. And that is my distance downrange. So the distance horizontally from my starting position. Question E asks us to determine the maximum height. Now height, that is a y value. So that means we come up here and we look at our y equation. When we see that word maximum from an algebra context, that means the vertex. And since the y equation is quadratic, we have a formula for the vertex. That x value at the vertex, or the t in this situation, is going to be negative b over 2a. Now, if I calculate this value, my output is going to be t, time. Are we asked to answer when? No, we are asked to find the maximum height. So after we find that time, we'll have to plug that back into the y equation in order to determine what that maximum height actually is. One other note, going back to part B before we start this problem, where do you think the maximum height occurs? Is the maximum going to be at t equals 2 seconds? So it goes up, it gets higher. Is this the max? Can we assume that? And the answer is no, but it's probably somewhere near 2 because it's going up, there's a high value, and then it starts going back down. If I had to predict, since these values are closer, it's probably somewhere between 2 and 3 seconds is when we reach our max. Back to the question at hand, I'm going to find t equals negative b, that's negative 50 root 2 over 2 times a, which is negative 16. So negative b over 2a, that gives me an output value of t equals 2.209708691, or rather just 2.2 seconds. Again, when we use this function to calculate the actual height at that time moment, you want to make sure that you're using a value with enough decimal places, trying to use that answer button on your calculator. And now if I plug that value into my y function, 60 plus 50 root 2 times 2.2 minus 16 times 2.2 squared. I'm going to type this in my calculator, and I'm not using 2.2. I'm actually going to use the answer button, which keeps all of this information. And I get an output height of 84.25. That would be 84.25 feet high. That's what represents my maximum height. And let's take this number here and compare it with what we had back here. So that max height is 84, so it occurs just after 2 seconds. 84 is occurring just after 2 seconds at 2.2 seconds. Now we're going to look at graphing this Cartesian plane curve, which is represented by these two parametric equations that we set up in part A. So you want to make sure that you are in your calculator and you're in parametric mode. So x sub 1 is going to equal 50 root 2 t. Y sub 1 is going to equal 60 plus 50 root 2 t minus 16 t squared. And once you have that typed into your calculator, it should look like this. Now, we can't automatically jump straight to the graph. One thing we need to make sure that we do is we set our window bounds as well as the interval for our t values so that we get the correct graph. Going into the window button, we need to set our t values to go from 0 to 4.5. And that 4.2 or that 4.5027, that's coming from the time when the ball hit the ground. Okay? So we found that time within the problem. So that's our restriction on t. This problem only exists for t equals 0 to t equals essentially 4.5. Set the t step as just 0.01 100th. Now let's think about our x values. What should my x's be between? I set my x to go to 400, and that's because we found that the horizontal distance was 318. So 400 is just a little ways beyond 318. I left a little bit of my x-min, so you could see to the left of that y-axis, and I counted my x's by 10, so it's going to make a tick mark every 10. My y-min is negative 10, and my maximum height was around 85, so I put my maximum at 100, and I had my y-scale also at 100. So the graph this gives me looks like this. So you'll notice that the graph does not extend outside of quadrant 1. So if you don't set your t min and max up correctly, that graph will keep going. So in order for this graph to be limited or restricted to quadrant 1, that's what that t min and t max are doing. So if this was too big, the graph would have kept drawing down into quadrant 4 here. Now, comparing these t values to maybe some points from our table. So one point we can connect is we have that y-intercept at the ordered pairs 0, 6. My maximum, which was at roughly t equals 2.2, that maximum represents my x and y value, my horizontal distance from the start, from the initial position, and then my vertical distance. So once the ball is at its max height, we know we have traveled roughly 156 feet away, and we are roughly 84 feet above the ground. And then, of course, we recognize that when we hit the ground at 4.5 seconds, we have a horizontal distance away from where we started of 318, and that y value, even though this says 1.6 times e to the negative 7, that represents 0. So I hope that kind of helps you understand how parametric equations could help in an application setting. The main thing is, both x and y are limited by what these t values can be. As always, email me if you have any questions or concerns or you need some extra help. Good luck!